First, let's talk about the disease in question. I work on a disease called malaria, and malaria is a infectious disease of global importance. And just looking at the statistics from the WHO from 2010, we have over 200 million cases of the disease worldwide, and of these over 200 million cases, about 665,000 people succumb to this disease, mainly women and children from Africa. So it is a disease that it's something that we have to look into. And one of the problems that we are facing with malaria is that a lot of the parasites that cause malaria have become resistant to current drugs, and we call these anti-malarial drugs. So what we do to address this problem is to discover new drugs against the parasite. And it's important to note that of all the drugs that are existing now, the parasites become resistant to almost all of them. But if you look at old drugs that we feel may be useless today, what we've discovered is that if we change the dose of the drug, a new target of the drug becomes active. And what we've discovered with a very old drug called chloroquine, to which most parasites have become resistant to, if you increase the dose, the stomach of the parasite, which contains a lot of toxic molecules, will become very fragile and will burst in a very dramatic fashion, and the parasite dies very quickly to this higher dose. This dose is attainable in the blood. So we have discovered that the other compounds can also elicit this effect, can also induce this bursting of the stomach of the parasite, because as you know, chloroquine can be quite toxic. So we're trying to find new compounds that are safer for use, and we have discovered a couple of them to date. The other thing we've done is with our chemist collaborators, we have developed new tools for research, and these tools accelerate drug discovery. What we've done is that we have tagged, for example, chloroquine with a fluorescent probe, and this allows us to monitor the amount of the drug in the parasite by fluorescence levels. And we found that drug-resistant parasites have lower fluorescence, but if you add a new drug that blocks the pumping out function of the resistant parasite, the fluorescence levels go up, which tells you that the drug is working. So we have developed this very rapid tool to screen for compounds that restore the effectiveness of chloroquine, and these are called resistance reversers. So we hope that tackling the parasite on both fronts, looking at new drugs that attack new targets, and also finding new uses for old drugs by looking for partner compounds that reverse resistance, we can contribute significantly in our fight against malaria.